Okay, this is a continuation from Unit 4, Lesson 1. We left off with the different forms of radiation, which are all part of the electromagnetic spectrum. To recap some things we did at the very end of yesterday's lesson, I was talking about the electromagnetic spectrum right here. It is an assortment of all the various forms of radiation that exist in our reality. And of all the various forms of radiation, which I have here, there's only one that we are capable of seeing, and that is called visible light. Visible light is all that our crappy human eyes are able to see. And it's broken down like there's a mnemonic device called Roy G. Biv. You got red, orange, yellow, green, blue, indigo, which is like a super dark blue, and then violet. Those are all the colors. That's all that we can see. We cannot see radio waves. We cannot see UV rays. We cannot see X-rays. We cannot see infrared or gamma without technology. There are technological advancements that help us see infrared. Has anyone ever seen the movie Predator? You know, the guy with the little, he's got the dreadlocks, the alien. There's this movie where this alien is hunting people for sport. And I had a picture ready because I'm actually kind of teaching this kind of stuff to my AP bio classroom. I'll show you guys here. Let me switch over to the internet. We use infrared for weather. Typically, warmer colors represent warmer air. Cooler colors represent cooler air. In the Predator movies, this is how the alien actually sees his prey. You can see in infrared. This is also how pit vipers, like a rattlesnake or a water moccasin, can actually see their prey. They see the body heat. This is another example of infrared. It's something I just thought of in case any of you want to run from the police one day. Hopefully you don't do that. Infrared camera police. I watched something in Hillsborough County just recently where they were tracking down people that were doing donuts in a parking lot where they were racing, which is illegal, and Hillsborough County is really cracking down on it. They were showing street level where everybody's screaming, hollering, recording, driving around dangerously, and up in the air you had a helicopter probably several 100,000 feet in the sky with a camera pointed at all these people, and they were talking to the police officers that were hiding down on the ground saying, okay, we got two vehicles, two people in each vehicle. Oh, now there's a third one, and they can see it because your body heats up like this. You got night vision on the left, but then there's thermal. That's infrared. This is also used for something that happened about, geez, I feel like 10 years ago. You guys are not that old. Have you heard of the Boston Marathon bombing? You remember hearing about that at all? Well, what happened is these two brothers they set up these bombs to go off, hurt a lot of people, and police officers found and killed the older brother because he pulled guns on the cops, and the cops defended themselves and neutralized him. But they couldn't find the younger brother, and they knew he was in the area. So they had the helicopters up in the sky trying to find him. And this one helicopter found something very odd. It's like, there's a heat signature coming from a boat parked in someone's backyard. That's weird. Go check that out. And it was the actual younger brother. And to this day, he's in jail because they caught him using the infrared camera. So that's infrared technology. A few others I want you to see. Let's do UV radiation. UV radiation is what actually burns you when you're out in the sun too long. You get a radiation burn. If you put your hand on the stove, that's a thermal burn. That's heat. If you got burned by some chemicals, that's a chemical burn. Radiation burns can also damage your skin, and they can damage your tissues. See if I might be able to find any. No, just basic like UV damage. UV damage can age you. You guys all go to the beach, you hang out by the pool, you want to get a good tan, all that stuff. Just be careful how long you're out there, because when you get to my age or your parents' age, that damage will come back and it can age you big time. You can look like you're 50 when you're actually 30. So UV damage does take a toll. Next one is X-rays. We use X-rays all the time to take pictures of bones and whatnot. We can't see it without technology, an X-ray machine, but they're a very powerful form of radiation. When you get your pictures of your teeth and your gums photographed with an X-ray camera, it's one quick little zzz, and that's it for about a year. You only get one X-ray every year because you don't want to get too much X-ray exposure. And then the biggest one, the most damaging, are gamma rays. There's something called a gamma ray burst or a gamma ray pulse. This might keep you up at night. When a supernova blows up, which is a star, an exploded star, it releases a gamma ray burst through space. Anything in the path of this gamma ray burst is immediately destroyed, just gone. If Earth happened to just be in the path of a gamma ray burst, see ya. We wouldn't know what hit us. It would be gone before we even knew. We would be gone before we even knew. I think that's probably, there it is, a gamma ray burst. It's just a beam of incredibly powerful gamma rays that will just destroy anything in their path. And those are emitted from a supernova. So, great bedtime story. That'll definitely keep you up at night. Nothing you knew about it, though, so why worry? All right, so let's get back to this. Okay. All right, where did we leave off? All right, let's talk about characteristics of waves. Wait, did I put a... Yeah, okay, I did. I want you guys to check this out. I'm going to zoom in on that. This is the electromagnetic spectrum. I want you to get really familiar with this because you may see this on your test. You will most likely see it on your notes. I try to find one that was displayed the same way as it is in your textbook. I like you to start here. This side is the weakest. Radio waves are the weakest form of radiation. We have radio stations all over town. If you listen to 93.3 FLZ, listen to 101.5, all these various radio stations, they're carried on a different frequency. And that's when you change the channel. Those numbers actually mean something. I'm going to give you your homework, which is based on the local radio stations. But radio waves and television waves are the weakest. Before you guys were even born, TVs used to look like this. They call these rabbit ears, and they had antenna, just like antenna on your car, just like antenna on phones. And they would receive the television broadcast over the radio waves. So radio waves can also carry an image, and that's what was used. In fact, nowadays, if you don't want to pay for cable, but you want to have some sort of television, there are still channels that are carried on radio waves. And I can probably pull it up on Walmart right now. If you buy this antenna, it looks like a square, but it's very flat. Y'all ever seen these before? You stick it to your window somewhere high, and then the other end goes to your TV, and you can actually get some channels. But that's modern day antennas. After that, you have microwaves. Microwaves are the a little bit stronger than the radio waves. So the same microwaves you use to heat up your food. You then go to infrared. I just showed you what infrared is. And something I want you to really appreciate is this little tiny sliver right there. That's it. That is the only part of the electromagnetic spectrum that our eyes are capable of seeing. And that is the color spectrum. Now, knowing that over here is the weakest and over here is the strongest, what color has the weakest frequency, or what color is the weakest color, the weakest radiation? Red. Red is the weakest. What color is the strongest? Violet. And the way that I remember that when I was in chem is violet is violent. It's the strongest color. These numbers are the wavelengths, which I'm going to teach you today. The higher the number, the weaker the wave. So you go from 700 to 650 all the way down to 400, and really that's 380 right there. The stronger, or the higher the wavelength, the weaker the wave is. So if you look here with frequency, you got 10 to the 8th and 10 to the 9th. These numbers are getting stronger as you go from left to right. Then you have ultraviolet. Then you have X-rays, And then you have the strongest form of radiation is gamma. This is the electromagnetic spectrum. This is in your textbook. And this is what we're going to continue talking about today. And what I'm going to focus on mainly is wavelength and frequency with you guys. All right. So let's continue. Characteristics of a wave. I'm going to draw two waves. All right. I'm going to draw a red one and a purple one. Let's say that's the color red. That is found in sunlight. Sunlight has all the colors of the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Whenever sunlight goes through a prism, like water droplets in a rainstorm, you can see all the colors. Red is the weakest color. Violet is the strongest. And here's how a violet wave looks compared to a red wave. There are characteristics to both of these waves. Every wave has the same characteristics. They're just in different measurements. The first characteristic I want to go over with you guys is wavelength. Wavelength is exactly what it sounds like. It is the distance between two waves, the length of two waves. Now think back to Unit 1, metric system, the SI system. What does the majority of the world use to measure distance and length? Meters. That's right. So this is going to be measured in meters or centimeters or nanometers, something meters. All right, let's see if y'all can impress me. We're in Unit 4. I'm going to ask you a Unit 1 question. Impress me. A centimeter. Is that bigger than a meter or smaller than a meter? How much smaller? 1/100th. Okay. Nanometer. Is that bigger than a meter or smaller than a meter? Okay. Is it bigger or smaller than a centimeter? How much smaller than a meter is a nanometer? 1,000 would be a millimeter. Keep trying. 100 would be a centimeter. How many? A billion. A nanometer is a billion times smaller than a meter. All right. So, last thing, guys. The symbol for wavelength is a Greek letter. That is the Greek symbol. It is called lambda. That's the Greek letter. It looks like an upside down Y. It is called lambda. So how do I find what a wavelength is? Well, I wanted to draw in blue for a reason, so I can label this for you guys. I like you to go to the red wave. From here to here, in the space between, that's a wavelength. The distance between two waves. You go to the purple or the violet wave here to here. That's the distance between two waves. That's also a wavelength. So just use your own eyeballs. Which color has a longer wavelength, red or violet? It's that simple. It's that simple. All you gotta do is look. Let me ask you this. Ready? 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 What color would have a longer wavelength? Blue or green? Blue. Remember, the closer you get to violet, the stronger you get. The closer you get to red, the weaker you get. How about what color is stronger? Orange or yellow? No. Okay, what about orange and red? Good. Red is the weakest. Violet is the strongest. All right. The other characteristic, I'm going to change up my colors here. What color should I use? Let's do gray. Is frequency. When you turn on your radio in your car and you listen to the different radio stations, what you are doing is you are turning your radio to the different frequencies. 93.3 is a frequency. 101.5 is a frequency. 104.7 is a frequency. 93.5 is a frequency. Those are all different channels, but in science, those are frequencies. This is defined as the number of waves that pass a given point per second. It has three different forms of measurement. It is measured in hertz, which is capital H, lowercase z for an abbreviation. It is measured in waves per second. Or it is measured in the reciprocal of a second. I want to give you guys an example of how to write this. And so this always trips people up a little bit. What I want all 31 of you to realize is that whenever you see the word per, P-E-R, like miles per hour, waves per second, whenever you see per, you draw a line, like a division line. Got it? So let's say that you had a radio station that was at 652 hertz. You write 652 followed by HZ. And recall what I told you in Unit 1. When I capitalize, you capitalize. When I lowercase, you lowercase. There is a reason behind it. For waves per second, you would write 652 waves per second. You don't write waves, you just do the number per s, per second. And then this last one, the reciprocal of a second would be 652 s with the power -1. That is how you write them. They all mean the same thing. They all mean the same thing. 1 hertz is 1 wave per second, is 1 reciprocal of a second. And then finally, when it comes to frequency, it is also a Greek letter. It looks like the letter V. Nick, this is not the letter V. This is the Greek letter nu, N-U. It looks like a V. It is not V. And then finally, you have amplitude, which we really don't talk about too much in our measurements, but I'm going to show it to you. This is simply a wave's height from origin to crest or trough. Crests go up, troughs go down. So when you guys are done writing that, I'm going to go back up to my two waves and I'm going to see if you can tell me which one has a higher or lower frequency. And the amplitude is really just how high the waves are, how low the waves are. Okay, so let's go back up to our two waves. Let's see, Madeline, which of those two waves do you think has a higher frequency? What that means is how many waves pass a given point per second? How frequently does it happen? Like if I asked you, how frequently do you blink in a day? You'd probably say several thousand a day, maybe tens of thousands. Frequency is just how often it occurs. Which one of these two waves do you think passes the same point the most? Yes. So with this purple wave, everybody, this has a high frequency. And Madeline, how would you describe its wavelength? Long or short? Yes. Guys, a high frequency means a short wavelength. That's always going to be the case, always. If the frequency is high, the wavelength is very short. That means the wave looks like this. Look at me. It's like this. It's very rapid. Very short distance between waves, and it's going really quick. Now, Caden, how would you describe, or Kellen, how would you describe the red one? Would you say the frequency of the waves is high or low? And how would you describe the length of the wavelength? Yep. So we say low frequency, long wavelength, or high wavelength. These waves are weak. If I asked you, if you had to choose, what do you want to get hit by? A low frequency wave or a high frequency wave? You want to get hit with low. Right now, 93.3 FLZs, radio waves, are hitting your body. Right now. Do you feel it? No. Radio waves are harmless. If they were not harmless, we would not allow them to broadcast. There would be no radio stations. It would be bad for our health. Do we let x-rays be fired at you all the time? No, because we know that's dangerous, so we don't let it happen. But what I want you guys to gather from this is that low frequency and long wavelength are always together. And then high frequency and short wavelength are always together. You will never have low frequency and short wavelength. That doesn't work. You will never have high frequency and long wavelength. Never. These are the two that, this is how they're always paired. Let's put it like that. Okay. So now let's talk about all forms of radiation. I mentioned this yesterday. I want to continue on this. Travel at the speed of light. And the number that in speed of light is going to be represented by the letter C. You guys have to remember this number. C equals 3.00 times 10 to the 8th power. And this is going to be meters per second. That's metric. I like to give you guys about 30 seconds. Can you change that number from scientific notation to standard notation? If it's 10 to the 8th, how many spaces did the zero move? Or I shouldn't have said zero. Let me start over. If that's 10 to the 8th power, how many spaces did the decimal move? It moved 8 times. Did the decimal move 8 times to the left or 8 times to the right? No. The decimal moved 8 places to the left. So what I want you to do is I just want you to reverse that. So the decimal moved 8 places to the left. Where do you need to move the decimal to get it back into standard notation? Go back to the right. How many times? So do that. You have about 30 seconds. You have to be able to perform this. You will be asked to convert scientific notation to standard notation. Here's the logic I'm trying to impart on you. If it is 10 to the 8th power, that means that the decimal moved 8 places to the left. I want you to reverse that. Move it 8 places to the right. Do this now. Right, Aiden? Try it. Jackson, try this. Are you doing it? Are you just playing? This is scientific notation. Try to see if you guys can get into standard notation. So you got 3. 1, 2, 3, 4, 5, 6, 7, 8. And let's double check that. The decimal is right here. 1, 2, 3, 4, 5, 6, 7, 8. Nailed it. I'm going to put some commas in there. Feel free. What number is that? 300 million meters per second. That's how fast light travels. What do you suppose is easier? To say 3 times 10 to the 8th or 300 million? We use scientific notation because it just makes the numbers more manageable. So I want to do a few exercises with you guys to see if you can figure out the speed of light. Let's start with something easy. Yes, Jad. Let's start with something easy with the moon. The moon is 1 light second from the Earth. So if Tristan was on the moon and he and I were having a conversation using radio waves, are radio waves a form of radiation? So what speed do they travel? Speed of light. The moon is 1 light second away. So if I say Tristan's on the moon, I'm on Earth. Tristan, how's the moon? Over. How long will it take for him to receive that message? 1 second. So 1 second later, he gets the message. And he says, "It's good, Mr. Thorson. How's Earth? How long will it take for his message to get back to me?" So if he and I would have a conversation, what's the round trip of the conversation from him speaking or from me speaking, him hearing it, and him speaking back to me? 2 seconds. That's 1 second or 2 seconds round trip. Let's go to Mars. I always forget this one. Let's see. How many light minutes are between Earth and Mars? 12 minutes and 42 seconds. Okay, get your calculator out. You ready? Remember that minutes and seconds will only go up to 60, but your calculator, so you might want to break this down to 60. What is 12 divided by 60? Or 60, no, 12 times 60. 12 minutes is 720 seconds, and just add another 42 to that. So how many seconds does it take to talk, or how many seconds does it take for light or any form of radiation to travel from Earth to Mars? How many seconds? Here's what I want you to do. If you didn't get what I did, I said 12 minutes and 42 seconds. That's how long it takes for light to go back and forth between Mars and Earth. So here's Earth. Here's Mars. The distance is 12 minutes, 42 seconds. I want you to put that entirely into seconds. So how many seconds are in 1 minute? Multiply that by 12. What do you get? Add another 42 seconds to that. What do you get? 762. Okay, so we got it. 762 seconds. So if Nella was on Mars, and I said, "Nella, how's the red planet? How long will it take for her to get my message?" 762 seconds. That message is just traveling through space at the speed of light until it gets to her. And then she gets my message. And then she says, Mars is kind of cold. How's Earth? How long will it take for her message to get back to me? So what is the round trip conversation? How long will that take? What would you do? What math would you do? 762 times 2. Now divide that by 60. See how many minutes that is. 25.4 minutes. That is not 25 minutes and 40 seconds. That's just 25.4 minutes. It takes about 25 minutes for a round trip conversation on Mars to go. Now, here's something else I want to talk about. The distance between the sun and the Earth. The sun and the Earth is, I'm going to just round it up. It's about 8 minutes. How many seconds is that? What math would you do? Olive? So what's 8 times 60? Was it? 480. I want you all to turn around right now. Look back at those outside. What's lighting up the Earth out there? That sunlight is 8 minutes old. When you go outside and you feel the heat of the sun, or if you like to lay by the pool or the beach and you feel the sun on your skin, how old is that radiation? How old is that sunlight? It's 8 minutes old. If the sun blew up right now, when would we know it? 8 minutes from now. When the sun sets, when did it actually set? 8 minutes ago. So if you ever don't do this, you're not supposed to look at the sun. But if you were to look at the sun and it exploded now, and you looked at it, would you see the explosion? No. What would you be looking at? The sun. You're looking into the past. This is our best form of time travel. This is looking into the past. So if the sun blew up right now and you had like special sunglasses and you could see it, right now the sun would look like the sun. When would you actually see the explosion? 8 minutes from now. That's kind of like time travel. So what I want to talk about next is a star called Betelgeuse. Yes, Alex?
Does the force of gravity travel at the same speed as light, so we can be in orbit for 8 minutes?
No. That's another factor. It does not travel the speed of light. All right, I need to look this one up. I'm pretty sure I know it's like 642 and a half. Hey, Google, what is the distance between Betelgeuse and Earth? It's not 700. It says around. Hold on. I want to get the exact one. I'm just Googling right now. Betelgeuse distance from Earth, light years. Give me the right number. 642. Yep, I was right. All right, so the distance between Betelgeuse, which is a giant star, and Earth is 642 years. So let me tell you what that means. We talk about light years. A light year is the amount of time it takes for light to travel 1 year. So if we were to fly to Betelgeuse, this big star, huge star, that's part of the Orion constellation, it would take us 642 years traveling at the speed of light to get there. Do we have the technology to travel the speed of light? No, we barely have the technology to travel the speed of sound. So let me show you where Betelgeuse is. Let me switch my screen. Let's Google the Orion constellation. If you look up in the sky tonight, not as many people do as they should. This is the Orion constellation. It's really hard to miss. And that website's taking forever, so I'm just going to zoom in on it. That's Orion. Anybody ever see the movie Men in Black? They talk about Orion's belt. There it is. One of these stars is called Betelgeuse, and it is a giant star. Let me see where it is. Orion, Betelgeuse. Which one is it? Okay, it's Ryan's shoulder. It's the Orion shoulder. You got one arm holding out the shield. You got the other arm holding his arm up. It looks like Betelgeuse is his shoulder. I always thought it was his foot. So let me show you just how big Betelgeuse is. It makes our star look like a speck of dust. It's big. So that's Betelgeuse. It's a red giant, I believe. Here we go. This will kind of give you some perspective. If the website will open. That's a crappy website. Let's zoom in. Okay, that's Betelgeuse. That's Orion's shoulder. That's our sun, right there. That's it. So this is an enormous star. If you go outside and you look at Betelgeuse tonight, how old is that light that you're looking at? Say it again, Kellen. Last night I went up and looked at Betelgeuse. That light is 642 years old. It is traveling at the speed of light, and it takes 642 years for it to go from it to us. So if Betelgeuse exploded right now, when would we know it here on Earth? We would know it in 642 years. That's how crazy this is. There are stars out there that are 9 billion light years away. So how old is the light that you're looking at when you see those stars? 9 billion years old. This gives us an idea of just how old the actual universe is. The universe isn't a couple thousand years old. It isn't a couple hundred years old. It wasn't born yesterday. In order for that light to travel through space for billions of years, space had to have been here for it to travel. Yeah. Yes. Wait, how many years? Yeah. I've actually heard that before. If you didn't hear what he said, dinosaurs went extinct 65 million years ago. The tagline for Jurassic Park in 1993 said a film 65 million years in the making. What he's saying is, you were on a planet, and this planet was 65 million light years away from Earth, and you got your telescope. You're looking at that little blue planet Earth, 65 million years. If it's 65 million years away, 65 million light years away, you look at your telescope at Earth, you would see dinosaurs because you're looking into the past. Whenever we look at a star, whenever we look at a planet, we're looking into the past because its light is traveling through space. And all forms of light, all forms of radiation travel at that speed of light. Yeah.
Wait, do you grow slower?
That has to do with gravity. That's something different than what I'm talking about. That's more of a physics question, and I am not good at physics. All right, so what I want to do with you guys now is I have you about 5 minutes. I want to teach you how to do your homework tonight. So this is where your calculator needs to come in. This is about calculating wavelength and frequency. Here's your equation. All right. The equation that you'll be doing is going to be C equals lambda times nu, or in plain English, the speed of light equals wavelength times frequency. You will be given 2 of these values. You have to find the third. You'll be given 2. You need to find the missing variable. So one of the prereqs for this class is algebra. Not really, really hard algebra 2 kind of algebra, just basic algebra. Guys, if I have C equals wavelength times frequency, and I wanted to find frequency, how do I isolate it so that it is by itself so that I may solve for it? What do you do algebraically? You raise your hand. Divide both sides by wavelength so that wavelength crosses out, and your new equation is going to be C over wavelength equals frequency. What if I wanted to solve for wavelength? What would you do? Sawyer, what would you do if I wanted to solve for wavelength? Divide both sides by frequency. So it's going to be C divided by nu equals lambda. Okay? Now, everyone, if your answer is wavelength, what are some units of measurement that it could be measured in? Wavelength. Meters, mostly meters, or maybe a derivative of it, centimeters, nanometers. If your answer is in frequency, what are the 3 different ways that you can measure frequency? They're interchangeable, but you need to know that they're interchangeable. What's one? Hertz. What's another one? Waves per second. What's another one? The reciprocal of a second. And when you're doing speed of light, what is that measured in? Meters per second. Okay, I'm going to pass out your homework. And I did a practice problem for you on it so you can kind of get the hang of it. I'm going to stop recording now.